Oops, there you go. So the coefficient of determination is the very last thing we need to mention. So I had kind of talked about this before when we were talking about correlation coefficients, is that you notice that when we were trying to calculate them, there was this R on the calculator, and then there was this R squared. So the R squared is representing this coefficient of determination. And when we were looking at the data about houses and their sizes and their price, we said that, price could be a good predictor. Size is a good predictor of the price, but, sometimes there's other things that affect that price. We know that, like the neighborhood and things like that can affect the damages to the house. Does it contain its old woodwork? Things like that have a big impact on the actual value of the home. So that being said, what the coefficient determination does is it tries to determine how much of the variable you're looking at influences the data. So explained it in unexplained differences. So we consider the least squares line and the line y equals y minus. So not y minus, let's say it again, the y bar. So what we're saying here is we're going to draw this y bar here. So we're showing the mean of y's. So the mean of all those prices in that case. So for any point xy, x minus xy can be split into two parts. The first part, x minus xy, is the difference between the central value, let's try this again, x hat minus xy is the difference between the central value y and the predicted value y hat. This is called by the explained difference. So right here, remember that is my y, where my y hat's going to be. This is my y bar here. So this difference is an explained difference. So this is what we can explain from the data. So, and like I said, it's called explained difference, and it represents the difference explained by the least squares regression line. The second part is your residual. So it's that difference between y and y hat, is the difference between the observed value y and the predicted value y hat, which is your residual. So unexplained difference is residual. So what we have here is that we're looking at where the mean is. So if you're looking at y hat, your predicted value, its difference from the predicted value to the actual value is the residual. That is unexplained. The part that we can explain is the difference that happens between your y hat and the mean of all your data. So the second part, y minus y hat, is the difference between the observed value and the predicted value, which is just the residual. This difference is caused by factors unrelated to the least squares regression line, and is called an unexplained difference. So this is the part that is explained, essentially, by price. We can explain this difference here by price. This difference here, explained by other factors. So the difference that we see of a actual value and the mean, like I said, is part of it is it's going to be explained by that, simply by the data that you're looking at. Sorry, not price, footage. So that part is explained by the square feet of the house. So the price is explained by that, and then part of that is explained by other factors, and that is the residual. So price is explained partly by the price, by the area, which is my explained. And the rest of the price is unknown factors. So the part you really have to worry about is what the coefficient of determination is going to be telling us. So the better the least squares predictions are, the smaller the unexplained differences will be. We measure the size of an unexplained differences by squaring them and then adding them together. This quantity is called the unexplained variation. The explained variation is similar with the explained differences. So when two variables have a linear relationship, the correlation coefficient R tells how strong the relationship is. The measure most often used to measure how well the least squares regression line fits the data is R squared. The closer R squared is to 1, the closer the predicted value for the least squares regression line are to the actual values on average. The quantity R squared is called the coefficient of determination. And it can be shown by advanced methods that R squared is going to be your explained variation over your unexplained plus your explained. So it's your explained variation divided by your total variation. Thus, R squared measures the proportion of the total variation that is explained by the least squares regression line. So basically, this is my line. This is Y bar. This is your point. And this difference here, the part that we see here in the bottom, this part is going to come from your R squared. So it's going to be kind of like looking at all those differences and sort of averaging it out. So it's going to tell us how much of the explained variation is involved in our data. So if we look at the size of a house and its selling price again, we saw that R, as I said up here, is 0.9005918. If I square that, that gives me my coefficient of determination, which happens to be 0.811. So what this means is that 81.1% of the variation in pricing that I see in houses can be explained by a least squares regression line, and it can be explained by price. Or sorry, explained by footage. I keep saying that wrong. And explained by size. So because the least squares regression line is explaining 81% of it, that also means the size is kind of explaining 81% of it as well. So like I said, there's other factors that are going to be involved, but for the most part, like 20% of it is other factors out there that I don't know about, but I know what 80% of the factor is, and it's really that size that's controlling a lot of that price. So for each of the following values of the correlation coefficient, determine how much of the variation the outcome is explained by the least squares regression line. So in this case, we have R is going to be 0.6, and then R squared is going to be 0.06 squared. So that's going to be 0.36. So 36% of the variation that we're going to see is on the outcome variable is explained by the least squares regression line. Oops, second, trying to grab something here. If we got a negative correlation coefficient, when we square it, it's going to come out positive again. So I square it, this is going to come out to 0.81. So 81% of the variation that I'm going to see in the outcome variable can be explained by the least squares regression line. If it is 0, my correlation coefficient is 0, saying I have no relationship, well then my correlation coefficient, let's try it again. Yes, correlation coefficient, my coefficient of determination, there you go. My coefficient of determination is 0, so 0% of the changes that I see or variations of the outcome are going to be explained by the least squares regression line. And if R is 1, then R squared is just going to be 1, because that's going to be 1 squared. That means 100% of what I see, variations in my outcome variable or my y, can be explained by least squares regression line. Okay, so for this data, I believe our correlation coefficient was negative 0.874. So if I want to figure out my coefficient of determination, I just need to square that. And I'm actually going to need a calculator for this one. The rest I could do in my head because those are easy numbers. This is actually going to be 0.763876. So I'm going to round that to 0.764. So that would mean that 76.4% of the variation in average hours of sleep, so it's always going to be your outcome variable, is explained by the least squares regression line. Or you can say by number of suites. So other things are affecting, or not affecting, but are going into that calculation to figure out what is somebody's average hour sleep. And we know that number of suites has about a 76%, 76% of that variation we're seeing in sleep could be predicted using, like I said, could be predicted, not explained, I was looking there, could be predicted by how much candy this person's eating or how many sweets they're eating.